Hey folks, as part of the 15-year celebration of Amazon EC2, this is the evolution of Amazon Virtual Private Cloud, or our VPC fundamentals session. So we'll be covering a little bit of history, but then we're going to dive into all of the different components that make up VPC, including PrivateLink, Transit Gateway, NAT Gateway, and how all of those components come together to build or help you build your infrastructure on AWS. I'm Matt Lewis. I'm a principal solution architect here at Amazon Web Services, and let's jump in here. So first, I wanted to cover a couple of key releases. And so the first, obviously, what we're talking about here today is the August 25th, 2006 release of Amazon EC2. And so following that, there were a couple of other releases that I just wanted to call out, and we'll talk about the way EC2 used to work and the way VPC works today. In March of 2018, we released Elastic IPs. And so Elastic IPs are essentially public IPs that you can use in your environment. And so I'll talk about the difference between VPC and how Elastic IPs really work within that. In May of 2009, Elastic Load Balancing was released. And so if you think about what makes up the cloud or what makes up AWS deployments, the ability to auto scale and horizontally scale your infrastructure is immensely important. And so Elastic Load Balancing didn't come along until 3 years after EC2 was actually announced. In August 2009, Amazon Virtual Private Cloud was announced and made available for general availability. And we'll talk about that and how that really changed the way you build things on AWS. So let's talk about some of our evolution around some of the instances that we have here at AWS. So on the far left-hand side here, we have our C1 instances that were released in 2008. And so they were able to do 1 gigabits per second. Now, as we kind of see the progression here, in 2010, so 2 years later, we had our CC1 instances that had 10 gigabits per second capability. Now, from there, we basically head upwards from a performance perspective. So the C3s had lower latency, and we released enhanced networking, which helped, something called SRIOV, which helps with your instance-based networking. C4s had EBS optimized performance. Our C5s had 25 gigabits per second, and that was in 2016. So we've gone from 2008 and 1 gigabit per second up to 2016, where we have 25 gig capable instances. And then when we go from there, the C5N and the P4Ds released in 2018 and 2020 have 100 gig and 400 gig performance for your instances, which is amazing. I mean, to have an instance with that much performance is, was unheard of for me when I was, working in this industry from, back in 2008 using C1 instances up until 400 gig instances on the P4Ds today. Pretty cool stuff. Let's talk about EC2 Classic now and how that really looks like, and then we'll compare it to Amazon VPC. So EC2 Classic was essentially where you had the internet, and then we had some instances that you had the ability to spin up, like the C1 instances, and they would get a public IP. And so this was all out of Amazon's pool of public IPs. You'd get a public IP assigned to the instance, and when the instance went away, the public IP went away. That was pre-Elastic IPs. And so you'll notice here we're just spinning up instances in this general kind of population of instances. And that worked quite well, giving you the ability to scale by as many instances as you needed. But folks that were building data centers and building infrastructure on traditional means really needed more capability around the networking stack itself. And so now if we talk about VPC, which came along a little bit later after Amazon EC2. So VPC basically has, it's basically a region level construct where we've got a CIDR address range which is associated with the VPC itself. And so as we spin up the VPC, we essentially spin it up in a region. So then we'll create subnets out of that CIDR range that are then basically where we can spin up EC2 instances. So we've got instance A, B, C, and D in 4 separate subnets across 2 different availability zones in a single region. So the VPC itself is a region level construct, but we're deploying in our availability zones, which are essentially like fault domains, and you can think of them having shared redundant fiber feeds and power feeds, etc. But you're deploying in those fault domains or those AZs by using subnets inside a VPC. So we have other services that sit outside of the VPC, like Amazon S3, DynamoDB, Lambda, a bunch of others. And basically, what you used to do is connect through something like an internet gateway to those services. Now, before we get to that, I know that was a bunch. Let's just take a step back. This is the fundamentals session. And so we're going to talk about the different components that go into building up your infrastructure before we get back to the architecture that we started to stack together there. So let's talk about VPC concepts and fundamentals. So when I think about the concepts and fundamentals, I think of 5 main things. I think of an Amazon VPC that has addressing or IP addresses. I think of subnets. I think of routing inside of VPC. I think of DNS inside of VPC because obviously you don't want to be remembering IP addresses all the time. So DNS is important. And then I think of security. And so security is definitely something that's important when you're deploying on a cloud deployment and also in a data center as well. And we give you security mechanisms to secure your environment on AWS. So the first thing I'll do when I'm creating a VPC is I'll choose an IP address range. And so in this case, we've got a 172.31.0.0/16. And this essentially gives us roughly around 65,000 IPs in what's called the RC 1918 range. The RC 1918 range is a private range of addresses that aren't routed on the public internet. And so what that's going to mean is your VPC, all of your instances in the VPC are privately routed within that VPC using private addressing. And what you also want to think about is when you start with one VPC, you may grow to 2 or 3 or 10 or connect to your on-premises. You want to make sure that each VPC doesn't overlap with each other from an address standpoint. And we'll talk about that a little bit more when we get into peering. So the next step is really creating a subnet inside a VPC. And so we've got our CIDR range of the VPC. We've got our availability zones here. We're using our Dublin region, so EU West 1, where we've got 3 availability zones. And then we can create 3 subnets, 1 in each of those availability zones. Now you can create multiple subnets in a single availability zone. That's totally fine. I've just got 1 per availability zone here, just as an example. We do also have the capability to have IPv6 in a VPC. And so right now you can do dual stack IPv6 and IPv4. And basically what happens is we allocate a /56 out of Amazon's IP range to your VPC, and then you can create /64 subnets. And so what that looks like is we get this /56 for the VPC. We've then got these /64 subnets associated with our existing subnets here. And so this is dual stack where you've got IPv4 and IPv6 running side by side. We can also expand the range of the VPC. So we can add up to 5 CIDR ranges to the VPC itself. And so the 172.31.0.0/16, we could do a 32 or a 33 or something like that to add additional ranges to that VPC and give us more address space if you wanted. Okay, so the next important thing is routing within a VPC. And so when I think about routing, I think about how I'm directing traffic from my instances to maybe the internet or on premises, or how traffic's getting to my instances. And so what we have within a VPC and within a subnet are route tables. And route tables allow us to control the destination of our traffic and where traffic's going to be sent. So to start with, your VPC has a default route table or a main route table that essentially is what's used by default by all of the subnets inside that VPC. What you actually want to do is create multiple route tables or create a route table per subnet. And that's going to give you a routing domain per subnet and help you have a little bit more control over where you send traffic on a per subnet basis. And so if we look at a route table here, we've basically got this is dual stack. We've got our 172.31/16, and we've got our /56 range here as well for our IPv6. Okay, let's talk about DNS in a VPC. And so basically, when we start talking about DNS within the VPC, we have a resolver that you can use, and that will associate DNS names with your IP addresses as you spin up an instance, for example. And so you can essentially turn on DNS resolution and DNS host names within the VPC. Now, it gets a little bit better than that, where you can also use a private hosted zone within a VPC as well. And so a private hosted zone is essentially going to give you the ability to have a little bit better names for your DNS within the VPC. So you can have my example site associated with, in this case, we've got an A record of a 172.31.0.99, where essentially that A record is associated with our example demo host name, DNS name. So quite useful there. We also have Amazon's Route 53 resolver for hybrid clouds, where you can essentially configure endpoints for inbound and outbound DNS queries into your VPC. So that's quite useful too. Okay. So next is network security. So we have a couple of different mechanisms that you can use for network security. We have security groups, network access control lists, and then for things like visibility, you can use flow logs and traffic mirroring, which we'll talk about a little bit as well. And so security groups, firstly, you can think of them like firewall rules that are associated with your instances. And so if we have our VPC here, we've got our internet gateway allowing traffic to come into the VPC. And we've got maybe a two-tiered web architecture where we've got our web and applications in two separate tiers, and they may be in two separate subnets. And then we've associated two security groups with these instances. So our my web servers security group and my backend security group. So for the web and for the application instances. And so what we're doing here is we're allowing all traffic to talk to the web servers, because that's something that you probably want. You probably want your customers to come in and talk to the web instances, and you don't want to block those using security groups. However, what you don't want are folks coming in from the internet talking to your application, talking to your database, talking to the back end of the application itself. And so in this case, we've got allow only my web servers. So only the web servers can talk to the application servers. So we're basically doing some security group referencing here. And so what that basically looks like is this, where we've got two security groups. And so our web servers have our HTTP allow, it's basically like a default route, like a 0.0.0 to 0/0, allowing all traffic in. And then for our backends, we've got a custom TCP rule only allowing the web servers in on port 2345. Okay, so further on network security, let's talk about network access control lists. So we do have this mechanism called network access control lists, or NACLs, which are essentially stateless rules you can assign to a subnet. So the security groups are assigned to an instance and they're stateful. So any traffic going out is allowed back in. For network ACLs, the traffic is stateless. So you do need to allow rules on both sides. And where this could be useful is if you have two different groups administering your environment. You may have some application folks using security groups on your instances. You may have some networking folks locking down the network ACLs. And so this gives you a little bit more control. So NACLs versus security groups. Okay, lastly here on network security, we've got flow logs and traffic mirroring, which give you visibility into the traffic traversing your VPC. So if we start with flow logs, there's a couple of different sources here. We've got the VPC, we've got the subnet, and we've got the EC2 instance, or the ENI itself. And so we can basically take metadata for those sources and send them to different destinations. So we can send them to Amazon CloudWatch, or we can send them to Amazon S3. And so what a flow log basically looks like is some metadata of the traffic traversing your infrastructure. And so here we've got the flow logs. You can create a flow log for your VPC, for example. We're sending one to S3 and the other to CloudWatch logs. And if we have a look a little bit deeper here, the flow log contents themselves. So basically, we've got a whole bunch of different mechanisms that go into this. And I'm just going to fast forward here through this slide to build it out a little bit. But you can see we've got a whole bunch of different attributes associated with the flow log content. So the flow log version, the account ID, the source and destination IPv4, IPv6 address, the source port, the destination port. And so this is going to give you a log or some detail or some metadata of the traffic that's really traversing in and out of your VPC. And there's a bunch of different attributes there. Next up, we have traffic mirroring, or VPC traffic mirroring, where essentially we've got traffic coming in and out of the instance here on the left-hand side. What we can do is enable traffic mirroring for that instance and send traffic to a monitoring instance. So if we create a traffic mirroring session and assign that ENI as one of the sources, traffic is now going to get sent from that ENI to the ENI, or even maybe a network load balancer if we wanted to, of the monitoring instance or monitoring instances. And so what you're getting here are the real packets going in and out of the EC2 instance. So not just the metadata, but the whole packets, or truncated packets if you want it. And so you can basically build your own traffic analyzer. You can use open source traffic analysis like maybe Zeek or Suricata, or you could use many of our AWS traffic mirroring partners who have built integrations into traffic mirroring so that they can do analysis on the traffic that's being sent to them via traffic mirroring. So this is quite a useful tool. All right, let's move on to connectivity options for your VPCs. And so connecting to your VPC, you might want internet connectivity, or maybe not. Maybe you don't want internet connectivity. You might want to connect to other VPCs. So a lot of customers start with one VPC and then move into many VPCs in their environment. And so in a lot of cases, you'll want to connect those VPCs together. Lastly, we're not going to cover too much on this, only a little bit. Some of our other sessions are covering more of our on-premises connectivity, but we do have the ability to connect to your on-premises network via things like AWS Direct Connect and our VPN as well. So let's talk about internet connectivity, or maybe not. Maybe you don't want internet connectivity. So here we've got a VPC, we've got our instances, and we've got our route table. And so what we've essentially got is then an internet gateway, or an IGW, which gives us internet access. We then have a default route via that internet gateway. And what we'll do is we'll associate an elastic IP with that instance. Now, remember with EC2 Classic, you would just get an EC2 instance with a public IP, and that was it. With VPC, you get a private range that you use within the VPC, and then you can associate an elastic IP at the IGW. And it's funny, if you do an if config or an IP config on the instance itself, you won't see the public IP. You'll only see it at the IGW because that's a static one-to-one NAT that's happening at the IGW itself. And so here, instance A has direct internet connectivity and connectivity to other services or public services like S3 and DynamoDB and others. We'll talk about another mechanism to connect to those in just a second. Now, maybe we want our instance C to have to not have internet. We want our instance A to have internet connectivity, but we want instance C to not be able to be reached from the public internet. And so what we've got here are two different types of subnets. We've got our public subnets that have native internet connectivity, and we've got our private subnets that don't. And so in this case, our instance C has a default route to instance B, which is in a public subnet. And so what we might do is run a NAT instance, which essentially has some IP tables rules to do network address translation. We assign another IP to that network address translation instance, or NAT instance. And now we're sending traffic to the public internet. But what we've done is instance C doesn't have direct public access so that the public internet can't directly reach to instance C, whereas instance A does because it has that elastic IP assigned to it directly. Now, what might be a more scalable way to do things, instead of using a single instance for your NATing, you can use a NAT gateway. And so NAT gateway basically is a fully scalable service that operates inside the availability zone and gives you network address translation to the public internet. And so NAT gateway is a super popular service that we see customers using for this very use case. And so in this case, the route goes via the NAT gateway, not an instance. Okay. So let's talk about VPC peering, connecting to other VPCs using VPC peering. So we might have VPC A and then VPC B. And so in this case, we've got a 10.0 and a 10.1. So two different RFC 1918 ranges. With peering, we essentially have the ability to connect those two VPCs directly and natively. So it's a point-to-point connection between those VPCs. What we can also do is connect other VPCs to that same VPC. Or we can connect all the VPCs together in something like this in a full mesh type topology. Now, there's a couple of things to think about with VPC peering. So it is full private connectivity between your VPCs. You can peer across regions. And so this is immensely important if you want to have a multi-region deployment. You can peer those VPCs together across the AWS backbone between regions, between, say, Singapore and maybe Sydney, or maybe our Portland region and maybe Dublin. VPCs can also be in separate accounts. And so you can essentially run two different applications in two different accounts. Maybe they're totally two different customers, and you can peer those together if you need to. Also, your CIDR ranges must not overlap. So notice we're using unique ranges for all of those VPCs. You can't peer two VPCs together that have overlapping CIDR ranges. Now, the peering process itself basically looks like this. We have VPC A on one side wanting to peer with VPC B. The account for VPC A initiates a peering request. VPC B's account accepts the peering request, and then you create the routes in each VPC to connect to the other via the peering connection. And so routes basically look like this. We've got, in our VPC A, we've got a 1055/16 via the peering connection, or PCX 0E1FD, etc., allowing us to connect those two VPCs together. So next up is AWS PrivateLink. And PrivateLink is an interesting one where we saw a whole bunch of different public services, and S3 was our second service we launched right before EC2. There's another service we launched before those. But S3 was basically public, or public object storage. Now, after some time and with VPC, we saw customers building applications that were completely private, and they wanted private connectivity to those other services. And so what we did is release AWS PrivateLink, which essentially drops a set of endpoints into your VPC and gives you private connectivity to those services. And so we've basically got these endpoints that are consuming IPs from within your VPC range, so we don't even need to update our route tables. When you drop a private link or connect a private link to a VPC, you basically have connectivity via what we call the local route, or this 10.1.0.0/16. And so no additional routing is needed in our subnets. Now, we support over 92 services. I think the number's actually much higher than that now, since I created this slide. So there's many more services that we support private link connectivity to, and you can add a fine-grained access to your endpoints as well. Now, if we wanted to create an endpoint really quickly just to see what that looks like, so we're in the AWS console, we jump over to VPC, we go down to endpoints, and then we go over to create endpoint. And so here you can see the full list of endpoints that are available. And so you can see in the top right-hand corner, there's 93 services. I think it's even more than that now. We'd have to jump in the console for real and check it out. Now, we do also have a few updates to PrivateLink that have happened quite recently. So we do now have S3 access for PrivateLink, which is actually pretty awesome. Whereas before, what we basically had was a gateway endpoint. And so a gateway endpoint was different to an interface endpoint, which is what PrivateLink uses. So PrivateLink uses interface endpoints. And so here we'd have a gateway endpoint, and we'd have to configure a prefix list to S3. Now, the good news with this is data transfer to S3 didn't cost you anything going over a gateway endpoint, so that was good. However, customers essentially wanted to have access to S3 privately from on-premises, things like Transit Gateway, VPC peering, or VPN and Direct Connect, so from other VPCs or from your on-premises. And you couldn't do that through a VPC with gateway endpoints, because that was essentially what's called transitive routing, and a VPC doesn't allow you to transit through a VPC natively like this. So then we basically created interface endpoints for S3, and essentially what that does now is drops an interface endpoint into the VPC, uses the VPC range for the endpoint, and allows you to connect through to S3 natively. So now you can use this for hybrid connectivity for other VPCs, for via Transit Gateway connectivity into the VPC up into S3. The only downside is there's a data transfer charge for using PrivateLink versus using gateway endpoints. So something to keep in mind. You can also use PrivateLink to build your own services. And so we have a whole bunch of marketplace customers that do this and offer these services, or you can build a service in this case where we've got a customer VPC or consumer VPC on the left, and then we drop an interface endpoint in that VPC. We use PrivateLink to connect to an NLB or network load balancer in the service provider VPC, and you can front that service into this VPC on the left. Now, the beauty of this topology is you can essentially drop this endpoint into many VPCs that gives you many VPCs connectivity into the service that you've built. So it's pretty awesome. Now, a couple of notes here. You can tag endpoint services. Endpoints, just like S3 interface endpoints, are reachable over peering or direct connect and that sort of thing. And that's also applicable for other endpoints like we talked about with S3. But there have been some updates. So we have 450 plus ISVs and SaaS partners now that support interface endpoint services. So there's a whole marketplace around this. We do support private DNS names for internal or third-party services, and we also support fine-grained IAM permissions. We've updated some of our IAM permissions for endpoints as well. So definitely worth checking out if you're looking at building a service and offering it to many customers or consumers in AWS. All right, let's talk about Transit Gateway now. Transit Gateway is one of those things that we released in November of 2018, and it's something that gives you a lot more scale as far as your VPC deployments are concerned from a connectivity standpoint. And I say and beyond here because Transit Gateway is really a means for connecting VPCs, but it's also a means for connecting to your on-premises via VPN and direct connect as well. And we'll touch on that a little bit. So with Transit Gateway, we essentially have this type of topology prior to Transit Gateway, where we have VPCs that were peered together. We might have a VPN connection, and notice for each VPC, we need a VPN connection in this topology without Transit Gateway. So it was basically a one-to-one mapping where you had a VPC, you had a VGW, you had a VPN, and then the customer gateway or customer site. And for each VPC, you needed to build that VPN connectivity. The same went with Direct Connect, and this is prior to Direct Connect Gateway, but basically Direct Connect private virtual interfaces would connect to a single VPC, like you see in the topology in the diagram here. Now with Transit Gateway, we essentially built a mechanism for connecting many VPCs together. Now, before we get into that though, this is basically a peering topology where you'll notice we've got VPCs A, B, and C, and they need a route in their route tables for each peering connection. So we touched on peering before, and basically, if you're looking at building this full mesh type topology with VPC peering, now you need a whole bunch of routes in your route tables for each one of these VPCs. Now let's look at that from a scale perspective. So if you wanted to build a full mesh peering arrangement between all of your VPCs, it's really an n to the n minus 1 over 2 problem. And so what that means is if you have 10 VPCs, which isn't actually that many, we see customers with hundreds or even thousands of VPCs, but 10 VPCs, if we plug those numbers in, that would mean you need roughly around 45 peering connections. Now, if we had 100 VPCs, that would mean you needed 4,950 peering connections to do a full mesh between all of those VPCs. And that's actually not possible because we do have some limits that you would hit. So static routes per Amazon VPC route table is now 1,000. So it used to be 100, but it's now 1,000. So that's actually a little bit better. It's 50 by default. So you definitely want to increase that soft limit up to a hard limit of 1,000 if you need it. But you can also only have 125 peering connections per Amazon VPC. And so when we think about 4,950 for 100 VPCs, that's how many peering connections overall. That's how many you would need to manage. But each VPC would actually have 100 VPCs to its other 100 VPC peers to 100 other VPCs. It gets complicated. Let's talk about with Transit Gateway now. So with Transit Gateway, it basically becomes the central focal point for connectivity. And so the Transit Gateway is allowing us to connect everything together here. And so it sits in between our VPCs, our VPN connections, and our Direct Connect now, which is reasonably new. And so the Transit Gateway basically has something like this, where we have attachments to each of our VPCs and to our on-premises. Now, you'll notice the route here, we've got a default route via the TGW instead of having to have each of those individual routes. Now, the TGW also has a route table you can manage, and if you'd like, you can have up to 20 route tables within a transit gateway, which allows you to have a little bit of routing policy control around who can talk to who. A VPC A could be in the same VPC, for example, and so you can basically segment those out if you'd like. Now, there's three new terms when we talk about Transit Gateway. There's an attachment, which is the connection from an Amazon VPC to a VPN. A connection from the Transit Gateway to a VPC or a VPN or to a TGW. There's the association. So that attachment is associated with a route table, and that's to route packets from that attachment. And we also have a propagation, so we can propagate routes from an attachment into another route table. And so this is how you basically build that policy control through these three mechanisms: attachments, associations, and propagations. You can have 5 TGWs per account and 5 attachments or 5 TGWs per Amazon VPC. And you can do up to 50 gigabits per second per availability zone. And that's a burstable bandwidth. So basically, a TGW with its attachment has an attachment in each availability zone that you configure the attachment to, and you can do 50 gigabits per second per availability zone. Pretty awesome. Our VPN is capped at 1.25 gigabits per second. However, we do have what's called ECMP, or equal cost multipath. So you can actually send traffic over many VPN connections. And I've got a really quick aside on that in just a second. Okay, you can have up to 10,000 routes per transit gateway, which is pretty amazing, much more than the VPC route table. And here's the key one. Per TGW, you can have up to 5,000 attachments per account, attachments per region per account. And so your TGW can basically be connected to up to 5,000 VPCs if you wanted it to be. So that gives you a much more scalable deployment than just using peering. Okay. So I've actually got a quick link here for some detailed instructions on how to configure Transit Gateway, because I know there's a lot there. Feel free to take a quick screenshot of that if you'd like. Leave that up there for just a second longer, just in case you didn't grab it. Okay, so the Transit Gateway architecture now, we've got VPC 1, 2, or maybe N. We've got our attachments, and N could be up to 5,000 VPCs. We've got our on-premises connected to the Transit Gateway via a VPN. We might have a transit VPC with some instances using VPN and using equal cost multipath. So this is where you can have multiple VPN connections over multiple instances if you wanted to, and this is very common in SD-WAN deployments. And then you might also have a direct connect with, this is reasonably newish, where you essentially have what's called a transit virtual interface connected through to the Transit Gateway, and that's now bridging your on-premises into the Transit Gateway. So the Transit Gateway is really that central focal point for all of your connectivity in AWS. All right, let's bring it all back together and see what this topology looks like with everything we've talked about. So we have our topology from earlier, and this is where we kind of took a pause to cover a lot of the foundations and some of the other components that go into the VPC. And so if we build this out now, we basically have our route tables. We've got our internet gateway. We've got our default route again, and I'll cover this a little bit quicker because we did cover this already. We've got our NAT instance, or maybe NAT gateway connecting to the public internet. We've got our gateway endpoints allowing us to connect to DynamoDB or Amazon S3. And we talked about S3 gateway endpoints a little bit. We didn't talk about DynamoDB though, but you can use gateway endpoints for DynamoDB. We've got a VGW with maybe a VPN connection and a DX gateway. And we'll talk more about hybrid connectivity in one of our other sessions as part of the EC2 birthday sessions. And so we have direct connect via VGW. And notice we're building our routes on the left-hand side here. We've got VPC peering, which is our one-to-one connection to many VPCs. We've got our transit gateway, which can connect up to 5,000 VPCs. Or can connect to, we didn't talk about this one, but you can connect from a transit gateway to other transit gateways in other regions via transit gateway or TGW peering. And so now you can bridge all of your regions together 5,000 VPCs in one region, 5,000 VPCs in another region, all bridged through transit gateways. And transit gateways are a region level construct, just like VPCs. And so our transit gateway allows us to connect to VPNs or direct connect. We also have flow logs, which we chatted about briefly, where we've got S3 or CloudWatch as destinations for our VPC flow logs, which are like that metadata for traffic traversing your VPC. We've got PrivateLink and PrivateLink interface endpoints for services and things that you build or applications you build. So you can front end those applications with PrivateLink if you wanted to. We've got Global Accelerator, which we didn't actually touch on, but it's like a fully featured Anycast type service that runs out at the edge. There's a whole bunch of stuff that goes into routing and features you can use with Global Accelerator. And it's really good for building multi-regional deployments. And we also have traffic mirroring here inside the VPC. So sending traffic from one instance to a monitoring instance via traffic mirroring, or maybe to an NLB if you want to front many monitoring instances. We've got ingress routing for the IGW, which we didn't touch on too much. We've also got client-to-site VPN, which we also didn't touch on. And then lastly, this one's an interesting one. We've got AWS Outposts, which extends the VPC down to on-premises equipment that AWS provides as a managed service. So you can deploy a VPC at your on-premises site. Pretty awesome stuff. Now, this brings everything back together, and this is kind of our final architecture here, just trying to show a lot of the different components that go into building Amazon VPC and what that looks like. So you get a bit of a full picture or from a macro level, what a VPC can do. And there's a whole bunch of other things like that we didn't talk about, like Gateway Load Balancer, our AWS Network Firewall, and some other services that go into VPC. But I kind of ran out of room on the slide here, so maybe I'll try and fit those in another time. Lastly, we do have the AWS Certified Advanced Networking Study Guide. I'm actually one of the authors of this, so feel free to jump in there and grab a copy. I get 0 royalties, but it is a means for where you can find out some more information about some of the foundational services that we run in AWS. Unfortunately, we do need to make a second edition right now for Transit Gateway, which isn't included in there, and there's a couple of other things we'd like to add too. So maybe keep an ear out for that. We're thinking about that one. And thank you so much for coming along today. Lastly, for some Q&A, feel free to post any questions in the chat, just like you have been throughout the session. We're happy to hang around and answer any questions after the session here. Thanks so much. And happy birthday, Amazon EC2. It's been 15 years. I can't believe it, how time actually flies. Very cool. Thanks, guys. See you later.